We're going to go over the homework for logarithmic functions, at least this worksheet. And what we want to do is sketch the graph of y equals log base 2 of x. Now let's recall that this particular log function is the inverse for the exponential function 2 to the x power. And if we were to graph this function 2 to the x, let's notice that when x is 0, y is 1, and when x is 1, y is 2, and when x is 2, y will be 2 squared, which is 4. When x is negative 1, we get 1 half, and then negative 2, and so on. So the exponential curve will look something like this. Essentially, to let you guys know, trying to sketch this neatly on an iPad isn't so easy. But this is the exponential curve 2 to the x. The logarithmic function, what we're doing here, just to kind of review, is showing that across this line y equals x. If I switch my inputs and outputs, my x and y values, that first point would be right here, essentially. And the first point here, 0, 1, is now 1, 0. The second point, 1, 2, is now 2, 1, and so on. So I can get a curve that's going to start to look something like this just as a sketch. And that is sketching the log function with base 2 by just switching inputs and outputs like we discussed in class. And that's what I'd expect people to be able to do, is essentially you can get rid of your sort of framework here, but is essentially really just to graph this log function with base 2. It's just a sketch. You're going to do the same sort of thing here with the next question, and this question here in number 3 looks like they want us to sketch y equals log base 4 of x. Now, again, remember where this comes from. This comes from the function, or the exponential function, 4 to the x, where you have the inverse of 4 to the x power is log base 4. So let's import a graph here to get started. Yeah, we're just going to have to try this out here. Maybe we can use this information to review a little bit here. Let's go over this. The first problem, I didn't go over this in a lot of detail because we did this in class, but let's take a look at this exponential curve. Okay, when my x value is 0, I get 4 to the 0, which is 1. When x is 1, 4 to the first power is 4. When x is 2, we get 4 squared will be 16. When x is negative 1, we get 4 to the negative 1 power is 1/4. When x is negative 2, we get 4 to the negative 2 power, which is 1/16. That's very small. So to review this idea, again, we can plot these points. 0, 1 is here, and if I change this color, here's where 0, 1 would be. 1, 4. To the right 1, up 1, 2, 3, and 4. 2 and 16 would be probably way up here. So this growth is going to happen pretty fast. Now when x is negative 1, we're at 1/4, so that's over here. When x is negative 2, we're at negative 1/16. So if I had to sketch these points here, okay, very closely, we're going to get never cross the x-axis. We're going to get super big really fast. This is exponential growth. And so we're going to switch these inputs and outputs like we did prior in class. Let's get rid of some of these here. And remind you that when I switch these points, what I'm going to be doing is reflecting every point across the line y equals x. And it kind of looks a little like this. I'm going to sketch these curves. And so now if I change all these points over here to the right where my x is my y is my x, now change this. Switch them. This is now x, and this is now y. That would look a little bit more like this in black. 1, 0, 4, 1, 16, 2, 1/4, -1, and then 1/16, -2. So 1, 0 would be here, and let's change this color. All right, 1, 0 would be here. 4, 1, 1, 2, 3, 4, 1 would be up here. And then 16, 2 would probably again maybe be way out here. And then similarly, 1/4, -1, so it looks like it'll be here. And then 1/16, -2 would be kind of over here. So if I start to sketch these points here and plot them a little bit more carefully, okay, I'm going to get this kind of growth here, or this increasing kind of situation. And I will go to 1/4 and get very close, never cross the y-axis. So we are reflecting every point in blue for the exponential curve. This curve here is that's the 4 to the x power. And now reflecting about the line y is x, we get this log 4 of x curve. So I don't really need to have this messy, reference points here to turn in my curve. What you're looking at really is the log function. And again, notice that this function never crosses the y-axis, and the domain here is all positive numbers. So this is what we expect you to do to be able to just sketch kind of the graph of log 4 of x. Okay, so we made use of that little issue that's going on. And let's try to find here on the iPad if possible. Maybe it's right here. Let's see where this would be. We're going to look at this makes us 5. Now I won't go through the details because now this is log base 10. And this function is the inverse of the exponential function 10 to the x power. So that's going to get a little bit tricky to do. So we're just going to sketch. And as we sketch this curve, just remind you, you essentially have an exponential curve that kind of looks like this. It's not to any great detail. It's not accurate at all, because this curve grows even faster than the prior problem that we just did. And on a test, I just expect you to do to somewhat graph your log function here. This is a common log, by the way. We're just going to sketch this, and let me write it down over here. This is the curve y equals log 10 of x, and it definitely is not to scale. So we're just going to sketch that, get rid of the framework, get rid of the tools needed to sketch this curve, and now we're at log base 10 of x, the common log. Number 7, if you wanted some details here, y equals log base e now of x, which is also known as the natural log. E is your exponential number, which is approximately 2.718. So we're really not going to sketch this curve appropriately. It probably would be best not to even use graph paper because of the fact that it isn't very accurate. We can draw this a little bit by hand. We have this x-axis. We we have this y-axis. And let's kind of draw a little bit better y-axis, I guess. X-axis, y-axis. Now again, if we consider the exponential curve e to the x, it goes through this point 0, 1. It's a growth curve. It's a growth exponential curve because the base is larger than 1. And it might be better to sketch this with somewhat freehand and reflect every point about the line that we just drew here, which is the line y equals x. So 0, 1 is now at 1, 0, and we never cross the y-axis. And we draw essentially that reflection. And so what you're seeing is the graph of the natural log function. And that's a sketch, probably better without the graph paper because of the fact that as you go through particular points, it's very inaccurate. So to point back out here, it's very inaccurate if you look at the points we've gone through on this grid. It's not accurate at all. We did go through some level of accuracy here. The base here was 4. And we went through some accuracy here as well. Base is 2. But the higher the base, the more closer to that x-axis these log curves get. So we just want to sketch, and that's pretty much what I expect you to do on a test given a sketch. Now, the next kind of problems we have here are the following. Number 9. These problems here, for example, number 9, if we go here, they want us to evaluate the logs. And so now I have log base 10 of 100. I'm going to have to determine the value. When they say to evaluate, they really want you to really return a value. Now, in order to do this, we're going to have to use the definition of logs. So let's recall that log base b of anything equals some value. That this statement is equivalent to the base to the square power equals our triangle. So if we're going to evaluate any log, what we're going to have to do is this. We can use a shape, or we can use a letter. Sometimes I like to use a letter. Call that maybe t. And so what that means is we're going to have to really check this relationship. That this statement is equivalent to 10 to the t being 100. Let's go take a look. See what I'm talking about. I have this base. 10 is my base. So log with base b is written as b. 10 to the, this is now my t power here. So if I let that be t, I can say now 10 to the t equals that triangle. Oops, sorry, let's go back. 10 to the t equals that triangle, which is 100. So the triangle is inside the argument of the log function. So it's 10 to the t power equals 100. And we're going to use this. Now we don't have to use colors necessarily. We just have to solve this exponential equation by using properties of exponentials. And so let's notice that t to the second power can be described as, I should say 10 to the second power, the t power described as 10 to the second power, because this number 100 is written as 10 squared. Okay? And now I'm going to use another idea here, just to let you guys know, just to review this idea. I'm going to use this repeatedly, this fact, that if I have a base to any power, happy face power is base to a heart, then what I can say is that my powers are the same. So here's another fact we'll use. That a base to one power equals the base to another power. These are the same bases. This is an important idea. My b is the same. Then what that implies is that the powers must also be the same. And that's what we're using here to justify the fact that we can now say that my power here of t and 2, that means that t has to have the value of 2. And this is our answer. If I go back up here, I can now say that log base 10 of 100 is the value 2. So what we're going to do is we're going to use the definition here of log, this definition, combined with this fact, that if my bases are the same and they both have powers, then the powers must be the same. This is because the exponential function's 1 to 1. We discussed this in class, so this is a consequence of being 1 to 1. So nevertheless, we're going to use this repeatedly. And we're going to see here number 11, log 7 of 49, we'll say, is that t. By definition of log, this means that 7 to the t power has to be 49. That my base here, 7 raised to the t power, better equal that 49. Okay, let's go back and do that again. The 7 base, oops, got rid of it. The 7 base is here using the definition. Let's say here's a t power, here's a t. Better be the 49. Let's use another color. Not very good today. Let's use, I guess, what's not available. Let's use, we got blue. Let's use the green. Choose green. It's 49. So take a look at this. This is how we're using the definition here. And 7 to the t power now is 49. With the 49, you're going to always use properties of logs. In other words, try to write 49 as an exponential that has the same base as 7. So what we're saying here is 7 to the t power is the same as 7 to the second power. Exponentials with the same base. 7 and 7 and different powers. That implies, since exponentials are 1 to 1, that t is the value 2. So in this case again, t happens to be 2. And that's how we evaluate logs. So at this point here, I want to emphasize use your properties of exponentials. Number 13. Log base 8 of 1 over 8. We're going to have to evaluate this. Let that equal t. So then now 8 to the t becomes 1/8. So what we're going to try to do again is use properties of exponentials here on the right side so that I can hopefully describe here two exponentials with the same base. And if you thought about it from beginning algebra, that 1/8 is the same as 8 to the negative first power. So what I'm saying is that 8 to the t power is equivalent to 8 to the negative 1 power. Same bases implies that my powers are the same. Or I can simply say that t is negative 1. So that this answer here shall be negative 1. You could get rid of that t. And this is what we're using here. Again, exponential functions are 1 to 1. And that's really behind the hood there that's making this work. So let's try number 15 on the homework. We got log base 9 of 1. Now set that equal to t. And when you do, you get 9 to the t equals 1. So remember what we said, that on the right side here, I'm going to use properties of my exponentials. And if I thought about it, 1 could be described as, in general, any base of the 0 power. But if I'm going to use the fact that it has equal bases, I'm going to use the base 9 to the 0 power. And again, notice that same base, different powers, t and 0. This means essentially that t, the power, is 0. So that this answer here is actually 0. Using the definition of log to evaluate these logs. Number 17. Log base 5 of 5, we're going to say, is t. Using the definition, we can say 5 to the t is 5. And like I said earlier, again at this stage, use properties of logs, exponentials. Well, you might say, well, they already have the same base. Okay, but what power do I need here? If these bases are the same, and they are, right, 5 and 5, I have a power over here, t. The question is, what's the power on the other side? 5 to the first power. In fact, in general, any base to the first power is itself. So that 5 to the first power is going to be 5. Now what this means here for us is simply that t is the value 1. So I can say t is 1 because we have exponentials with the same base, 5. Right? These are the same right here, with different powers, t and 1. That means t has to be 1. So we've evaluated this log. The answer is 1. Number 19. Log base 16 of 4, we're going to call that equal to t. Use your definition that 16 to the t is 4. Now in the prior problems, the right side, we said, in the prior problems we said, okay, use properties of exponentials. And what you're going to discover is that, well, I mean, that's kind of not, we may be able to use some properties there for 4. We can write that as maybe a 2 squared. But here's what's happening with these problems. You don't have to only use properties on one side. You could use properties of exponentials on the other side as well. So we can use properties here. And we want to, again, write this with the same base. So let me go back. We want our bases here. This is base 16 and this is base 4. We want those bases to be the same. So on the left side now, I'm going to use some properties. Notice that 16 can be described as 4 to the second power on that left. Don't forget the t power is really there. And that's still 4 to the first. So I wrote 16 as 4 squared. Now, properties of exponentials say if I ever have a base to a power raised to another power, I keep the base and I multiply the powers. So I get 4 with a 2t power, and that equals 4 to the first power. Notice again, this time I have the bases the same. In the past I didn't. So I had to use properties to get that the base is the same. And now this says to me that 2t has to be the value 1. So if I write that as 2t is 1, divide both sides by t, I'm going to get t to be 1/2. So I can replace this t with 1/2, and I've evaluated this log. So I'm just using properties of logs here and a fact. It's 19. 21. We got log base 8 of 16, and now that equals t. You're going to use the definition. 8 to the t power is 16. And like I said before, at this point we would use properties of logs. On the left, or on the right, sorry, we started by saying, hey, use property logs here. Or, sorry, exponentials. And then use properties of exponentials here. What can happen now is we can use properties of exponentials on both sides. And so remember, the goal is to write an equation that has the same base. And so if we really thought about it, let's notice that 8 can be written as 2 to the third power. Don't forget to raise that to the t power. And 16 is actually 2 to the fourth power. So if I use properties on the left, this means 2 to the 3t is 2 to the 4. We now have same base, 2. And we have 3t and 4, meaning 3t equals 4. Divide both sides by 3. I get t going to be 4/3. So this t is going to be replaced with 4/3. Using the definition of a log and properties of exponentials to evaluate. 23. Log base 3 of 81. That equals some t value. Definition. 3 to the t is 81. And again, we can use properties of exponentials on this side, because 81 could be described as 3 to the fourth power. So what we have now, 3 to the t power becomes 3 to the fourth power. Same base. That means the powers have to be equal. That means t is the value 4. So I can now go back and replace. Let's write it down here. T is 4. Let's replace our t now with the value 4. This is number 23. And this is actually how we evaluate logs, is by using the definition. So that definition goes a very far, a long way. Let's go back to the original idea here. The definition is right here. And that's what we're using, combined with the fact that really, what I'm really saying is that your exponential functions are 1-to-1. And we're using that relationship as well. So definition and 1-to-1-ness went pretty far. Now, if we look at question number 25 here, to show you the power of the definition, they want us to solve a log equation. They want us to determine the value of x. So I got log base 6 of x is positive 2. And I'm going to put this in red. Use the definition. And what that means is my base 6 to the second power will be x. Let's try to go through this in the color scheme. Base 6, base 6. To the second power, equals x. Here's this x. That's the color scheme here. This is the actual definition in terms of colors. It's not really necessary, but it may help some people because it says 6 squared here is x, or x will be 36. Now, you solve this equation. Okay, 25, the instructions were determine the value of x, and here it is. 27, log base 3 of x is negative 2. Again, by definition, 3 to the negative 2 power is x. Now notice this. By beginning algebra, we know what 3 to the negative 2 power is. That's 1 over 3 to the positive 2 power, or simply 1 over 9. We have solved this equation for x. Number 29. Log base 16 of x is 1/2. By definition, 16 to the 1/2 power is x. Now, 16 to the 1/2 power is another way of saying the square root of 16. And so the square root of 16 is going to be the value 4. So here, x is the value 4. We have solved this equation. Log base 2 of x is negative 3. Use the definition. 2 to the negative 3 power is x, or x is 2 to the negative 3 power. X is 1 over 2 to the positive 3 power. X is 1/8. All by using the definition. (33) Log base 4 of x is 0. Use the definition. 4 to the 0 is x, or x is 1. There you go, number 33. (35) Log base 16 x minus 1 is 1/2. I won't write down use the definition, but 16 to the 1/2 becomes x minus 1. Or we can say x minus 1 is the square root of 16. X minus 1 will be 4, and if we add 1 to both sides, we find that x is the value 5. Now we solve this log equation. Now let's go back and let's notice. If we plug in 5 here for x, okay, let's note that this is a solution, that log base 16 of 4 does equal 1/2, because 5 minus 1 is 4. Now the important thing to know here is that this number is positive, and you can only evaluate a log, any base, for a positive number, because remember, logs aren't defined for 0 or negative numbers. They're only defined for positive numbers. So that's going to have to be a positive number. (37) Here we go. Log 16 of x minus 1. Oh, sorry. Wrong question. 37. Log base 6 of x plus 3 is 2. By definition, 6 to the second power will be x plus 3. Or we can say x plus 3 will be 36. Subtract 3, and x here is 33. So if I go back now, right in here, replace 33 for x, let's note we get log base 6 of a nice positive number, 36, is 2. That is a true statement. And more importantly, to point out to you that this must be a positive number for our value of x being 33 to be a solution. Okay, back here, x has to be a positive number, or I should say, let's go back. X being 5. If I plug that in back in here, 5 minus 1 is 4. It's positive. We have a solution. And that's number 37. 39. Log base 8 of x minus 1 equals 1. Use the definition. 8 to the first power is x minus 1. Or 8 is x minus 1. If I add 1 to both sides, 9 is x, or x is 9. Notice, if I plug in back here, 9 for x, here's what I get. Let's note. Log base 8, 9 minus 1 is 8, and that does indeed equal 1. The important fact is that this is a positive number. (41) Log base 100 of x minus 4 is 1/2. Use the definition. 100 to the 1/2 is x minus 4. Or we can say that x minus 4 is the square root of 100. X minus 4 equals 10. So when I add 4 to both sides, I get x equals 14. Now let's check. Plug in 14 here for x. Notice what we get. Log base 100. 14 minus 4 is 10, a nice positive number. Sure enough, that's going to give us a solution. And that's number 41. Now, the rest of these questions are to use properties of logs. So we discussed these properties. Log base 2, x cubed y. Now, you're going to use properties of logs here to write simply, and I'll put this in red, they're going to say to write as sum and differences of logs. So for the homework, we discussed, or I should say classwork, we discussed the three properties, the power rule, the product rule, and the quotient rule. So to start off by reminding you that what you should see here is, or notice here is, there's a product there. So because there's a product, this can be written as a sum. All because you have that product there. And then we're almost done now. Let's just notice here that we can use power. We can pull out that power. And so by the power rule, that's 3 log base 2 of x plus log 2 of y. And you simply wrote this log here as a sum and difference of other logs. (45) log base 5 of x cubed y squared. I want to point out again, there's a product here between the two terms. So we're going to use product rule. Product rule says I can write my log of base 5 as a sum. And here's the sum. So when you have a product here, we can write our log separate with a sum. I get to now use product rule twice here, or power rule twice, meaning power rule says I can pull out my powers as a constant. Pull out those powers as a constant and multiply it to the log. So that 3 now is here, and that 2 now is here, times log base 5 of x plus log base 5 of y. So this is kind of done in 2 steps in some ways. If you can see that, you use product rule here, write it as a sum, and then use power rule, pull out the powers, those constants. And that's that. That's 45. 47. Log x to the 4th over z squared. And again, it's writing this as a sum or difference of logs. Only this time you notice you have a quotient, so you get to use quotient rule. Quotient rule says you can write any quotient as a difference. So that's why you see this quotient here written as a difference now. And again, notice you have a power, so you can now use power rule. You can pull out that power 4, pull out this power 2. So you're going to see now, I'll put it in red, 4, 2, log x, that's really now minus log z. Practically done in 2 steps. That's number 47. 49. The natural log of the square root of x over y cubed. Again, notice quotient. So we use quotient rule. Log of square root of x minus log of y to the 3rd power. Quotient rule allows us to write this as a difference. Just want to point out to you that something interesting happens here. That the square root of x is written as x to the 1/2 power. And so what you should notice is you have log of x to the 1/2 minus that log of y to the 3rd. Power here is 1/2 and the power here is 3, so I am free to pull out those constants, pull those constants out, and you'll still have 1/2 here, constant, you'll still have 3, but this will be now log of x minus log of y. And that's 49. You have questions here like 51 from your homework that says use properties of logs to write as a single log. So you now have 2 log of 3 plus 3 log of 2. And here's the instructions. Write as a single log. So writing this as a single log, let me remind you that you're working in reverse, meaning you're going to use all 3 of your properties, the power rule, the product rule, and the quotient rule in reverse. So if you notice, it starts off with here a 2 and a 3. That those are my powers. So I'm going to put them back essentially. Those constants are now going to be powers. So 51, we're going to have it written this way. This is going to be log 3 to the 2nd power plus log 2 to the 3rd power. We're working in reverse. The constant times that log is now really your power inside that log. And point out to you another thing, that you have this addition. So if I'm going to write as a single log, as one log, I'm going to have to use now the product rule. It's log 3 squared times 2 cubed. So I'm going to write this sum now as a product. And you are done. So this can be described as log 3 squared times 2 cubed. I want to point out to you that we can actually, although you don't have to, evaluate. In other words, focus on this. This 3 squared times 2 cubed is 9 times 8, which is 72. So this is really the log of 72. Not that big of a deal, but nevertheless, that's valid. 53. 1/2 natural log of 9. Oops, sorry. Is that 53? No, it's 51. Okay, 53 is going to be this. 53. 2 log 5 minus 3 log 2. Again, you're working in reverse. Notice you have constant and a constant. They're going to be our new powers. So you got log 5 squared minus log 2 cubed. Now at this point, you might say, well, let's leave it as it is. There's a difference here. Let's use, in reverse again, the quotient rule. So this will be log of 5 squared over 2 cubed. You wrote this as a single log, and that could be fine. But what I started to say a little bit earlier here is that if you wanted to write 5 squared as 25 and write 2 cubed as 8, you can. And so what you're really looking at is log of 25/8. And that's okay too. So you can write it that way. So that's what I started to say earlier. This is 53. (55) 1/2 natural log of 9 plus 4 natural log of 1. Now, this problem is a little weird because the natural log of 1 is 0. So that's not even there. I'd never seen that coming, but it's true. And so I just have 1/2 natural log of 9. So remember, power rule says that 1/2 is a power. So I have 9 natural log of 9 to the 1/2, where I know this is square root of 9, which is the value 3. So I have the natural log of 3, and that's 55. (57), again, we're writing as a single log. You got log of x plus log of x minus 1. So to write as a single log, I'm going to have to write that sum as a product. So this is log of x times x minus 1, or simply log of x squared minus x, because we may need to distribute. You don't have to, but we could. And you're done. (59) log of x minus log of x plus 3. Write as a single log. You got a subtraction, so we're going to write this as a quotient. Log of x over x plus 3. You're done. Number 61. Natural log x minus 5 plus 2 natural log of x. We're going to have to notice first that I have here a constant. So if I'm going to write as a single log, I'm using my properties in reverse, meaning that constant now I can put back up in here as a power. And when I do, I get the natural log of x squared. Notice I have a sum. I'm going to write this as a product. X minus 5 times that x squared. I can think I'm done, or I can say this is really x cubed minus 5x squared. There you go. 63. 4 log base 5 of x minus log base 5 of x plus 2. Constant. Put that back in here as a power. So you get log base 5 of x to the fourth minus log base 5 of x plus 2. You're going to write this difference as a quotient. You're working properties in reverse. X to the fourth over x plus 2. So you wrote these here as a single log. And that's what you're supposed to do here, working with these logs. And that's your homework from this section.